Alrighty, let's go ahead and get started. So we left off last time and we were talking about the pressures involved in the thoracic cavity and how they change during a single respiratory cycle. As we kind of mentioned, the respiratory cycle is caused by that increase and decrease in volume. And those increases and decrease in volumes cause those pressure changes that cause the air to move in and out. When we increase the volume of the thoracic cavity, the pressure drops and air moves in. That's our inhalation. When we recoil those muscles or contract other muscles, the size of the thoracic cavity gets smaller, volume goes down, pressure goes up, and the air moves out. And we can put this together, these two things together, the muscles that we talked about and these pressure changes together to talk about this respiratory cycle. All right, starting first with our inhalation or inspiration. Again, we are first here just talking about a normal resting breath. As we talked about with that normal resting breath, inspiration or inhalation is an active process, meaning we are contracting muscles. And which muscles primarily are contracted during this process? Diaphragm. Are any others involved in this normal resting breath?
Intercostals.
Yeah, the external intercostals, absolutely. So the external intercostals can be involved. It is absolutely positively primarily the diaphragm. That's tiny and depressing. Let's do that again. This is indeed the primary muscle, but the external intercostals also help in this. And if we want to take an exaggerated, right, inhalation, we can use muscles like our sternocleidomastoid or pectoralis pectoralis minor, our scalenes, all of which can bring our ribs up nice and large. And all of this action, the flattening of the diaphragm, the increasing of the thoracic cavity, do what to the volume of the thoracic cavity?
Increase it.
Increases. And so what effect does that have on the pressure inside the lungs? There you go, Alex has got it, decreases the pressure. And when it decreases the pressure, which way does the air move?
In.
In. There you go.
It's kind of a generalization, but is it wrong to say that like most muscles above the diaphragm are for inhalation and then most below are for exhalation?
Well, so here's the problem with that. So I would say, again, you're right. As far as the generalization goes, that appears to be the case. However, the serratus anterior is mostly above the diaphragm, so that one doesn't work. And if you think about it, remember, our external obliques actually come up over the ribs as well. So it would also be above the ribs. So those wouldn't work that way. As far as inhalation goes, though, yeah, I think all of the inhalation muscles are above the diaphragm. That seems to make sense. All right. So yeah, I think based on that. So those would. The exhalation ones are the ones where it gets a little trickier. All right. All right, here we've done it with words. Here we can do it with the pretty picture. That again shows how we are flattening out the diaphragm, increasing the size of the ribs, swinging those ribs up, increasing the volume. And again, when you're taking a normal resting breath, as we talked about, we're talking about a 1 to 2 millimeter of mercury change. We're not talking about a huge change in movement because we're not talking about a huge change in air. So we talked about, we're only bringing in about half a liter of air as a result of this movement. And again, when we talk about that normal resting breath, the exhalation or expiration is passive. Oh, I'm sorry. I got sidetracked from the other question. Oksana, here's what I would say. It is our normal resting breathing is a reflex. It is a somatic reflex. So it is involuntary in that sense. Again, it's not autonomic. It is controlled by the somatic motor nervous system, but it is a reflex. And we'll actually talk about the mechanism that controls it. So your normal resting breath is indeed a somatic reflex, so that you don't have to think about, all right, now I breathe in and now I breathe out, any more than you have to think about blinking, right? You don't have to think, all right, now I should blink my eyes. All right, now I should blink my eyes again. Oh, I need to inhale. All right, and now exhale. Oh, and then I got to blink again, right? We'd be exhausted if we had to do all that. So luckily we have reflexes that can do this. But at the same time, we know it's somatic. We know it's a skeletal muscle, because if we want to, we can voluntarily control it. If I told you to take 3 quick, shallow breaths, right, you could do that very easily if you wanted to, or take and hold your breath and count to 10. You could do that very easily as well. So it is definitely skeletal muscle that we can consciously control, but our the medulla and also the pons. So again, we will get to the regulation of this, and we'll find that it is done in the pons and in the medulla. That is where this is occurring. There isn't so much a case where someone would have to do this consciously. If you think about that, that would be a very, very bad thing, because then you'd never be able to sleep. If you had to consciously think about breathing in and out, then you wouldn't be able to sleep, because as soon as you slept, you wouldn't be able to think about breathing, and you would die as a result of that. So yes, look, there isn't a condition that I know of. Now, obviously, if someone's muscles are paralyzed, then we can put them on a ventilator and then we can control it there. Or if there's problems with the regulatory centers that we'll talk about, they can be put on a respirator and we can breathe for them. But typically a person doesn't have to consciously think about doing this. Yeah, or an iron lung, absolutely. All right, so with our passive normal resting breath, we're just relying on the elasticity of the thoracic cavity, the elasticity of the lungs. We're relaxing the diaphragm, relaxing those external intercostal muscles. And when we relax those, right, then as a result of that, they go back to original shape, and it doesn't use ATP. Relaxing a muscle doesn't use ATP. When we do this, what effect is this going to have on the thoracic cavity? What happens to the volume? There you go. Oh, got ahead of me. Decreases. Excellent. And when that volume decreases, what happens to the pressure? Increases. And when the pressure increases, which way does the air move? Perfect. There you go. Out of the lungs. Excellent, excellent, excellent. All right. So again, very simple, very straightforward. And again, we have that pretty picture that shows this process as well. However, if your hand were to spontaneously combust, or a little less severely, if you needed to blow out some birthday candles, we can make exhalation an active process. When we do this, this is typically what is called a forced exhalation, where you're getting a very active process. This forced expiration or forced exhalation. In this case, this is an active process because we're contracting muscles. And which muscles would be involved in this forced or active exhalation?
Abdominal muscles.
Abdominal muscles, right? You can feel those tightening, the internal intercostals. And there was one more. Serratus anterior, absolutely. All of those are pulling the ribs down, right? Tightening and decreasing the thoracic cavity. And the real key to this is that it is a rapid decrease in volume. Because we are able to actively contract these, we get a very rapid decrease in volume that, of course, produces a very rapid increase in pressure. And of course, that leads to a very rapid, forceful ejection of the air. Of course, again, now because of COVID, you're not allowed to blow out your candles anymore. You have to use a fan or your hand or something like that to do that. But back in ancient times, you used to be able to spit on your cake. Now you're not allowed to do that anymore. So you can't do that forced exhalation to blow out your birthday candles. Unless you're by yourself. And if you have a cake and birthday candles by yourself, then that is sad. All right. Questions on that? All right, excellent. So we now know the mechanical events that are going to move the air into and out of the lungs. We now understand the pressure changes that are going to allow them to move into and out of the lungs. But we still have this issue where we have to get the air through the conducting zone to the lungs. And that relates to this concept of gas flow. Gas flow is the movement of air from one location to another. Now, the movement of air, just like we talked about with concentration gradients, are going to be influenced by pressure gradients. As we have talked about before, if I have two tubes, and let's pretend they're the exact same size, although I think my drawing of it isn't quite 100%. So there you go. I think those are pretty close. Let's go ahead and erase that. Over here, I have 760 millimeters of mercury. And over here, I have 100 millimeters of mercury. In which of these two tubes is the air going to move faster? Is it going to move faster? Are we going to get more flow on the top, or are we going to get more flow on the bottom?
More flow on the bottom.
Why on the bottom?
Low pressure.
Well, but remember, but things go from a high pressure to a low pressure, don't they?
Yeah.
So where's there a higher pressure?
The upper.
Top. 760. So now I've had an answer for each. Someone said the bottom, one person said the top. Which is it? Come on, give me some answers. All right, another top. Excellent. That's still not everybody. Why isn't everybody answering? Is it because you don't know? Or is it because you're clever and you realize I haven't given you enough information? Remember, things move based on a pressure gradient. What if I told you that on this side of the tube, it is 758 millimeters of mercury, and down here on this side of the tube, it's 10 millimeters of mercury. Now, which one is it going to be? There you go. Now most people have figured out it's the bottom, right? It's not the absolute pressure. It is the pressure gradient, the difference in pressure that makes the greater. Again, just like concentration gradients, the deeper the angle, the faster diffusion occurs. So the steeper the concentration gradient, the more rapidly air is going to flow. And again, it's directly proportional. So in this case, if I change this one from 758 to instead, I now made it 756, what would happen to the flow? How would the flow in this tube change with that change in pressure?
A little faster.
Okay, you could say slightly faster, but if you think about it, what was the pressure change before? What was the difference between the two environments?
2.
2. What's the difference between the two environments now?
From
4. So notice I just doubled the pressure gradient. So if I double the pressure gradient, what happens to the flow? Doubles as well, absolutely. I just doubled the speed of the flow. They're directly proportional. If I double the pressure gradient, I double the speed. If I half the pressure gradient, I half the speed. So these two values are proportional to each other. Flow is also inversely proportional to the resistance. Right? Resistance is the inverse of flow. So, and we'll talk about how we can affect resistance in a second, but let's just figure this out. So if I doubled the resistance, what happens to the rate of flow?
halves.
Halves. Excellent. So if I double the resistance, that halves the flow. Conversely, if I double the pressure gradient, oops, no, hold on. If I double the resistance, I half the flow, but conversely, if I double the pressure gradient, then I double the flow, right? So we're able to, in a physics equation, basically put this relationship with each other together. Directly proportional to pressure gradient, inversely proportional to resistance. Fun with physics. Now, this is true for our entire conducting pathway from our nasal cavity all the way down to our bronchi. But notice what they've done for us here is they've given us the stages of the branching. Notice the pressure is relative, the resistance, I should say, is relatively moderate in the oral cavity, in the esophagus, not the esophagus, in the trachea, in the primary bronchi. But notice here in our terminal bronchioles and in the rest of our respiratory zone, it's very, very low. Aren't these things tiny? If these things are super tiny, shouldn't they have a really high resistance?
No.
Yeah, think of it this way. If you're going to drink a shake, do you want a really tiny straw or do you want one of those big, huge barreled McDonald's straws? The big straw, because the more space, the less in contact with the surface of it you are, the less resistance that you have. So absolutely, those bronchioles are tiny, but remember also we have a massive number. So while each individual one may have a high resistance, when you have a million of them, there's almost no resistance to them at all. So those tiny bronchioles are very, very numerous, massive number of them. So as a result of that, the pressure is very, very, the resistance, I should say, is very, very low. Conversely, here we have a relatively low because we only have a few branches, structures, but they're huge structures, like the nasal cavity, like the larynx. So notice the highest resistance in our airways is in those mid-sized bronchi. In the mid-sized bronchi, somewhere around 7 or 8 levels of branching, they are now relatively small, but still few in number. if you think about it, this is also the area where we are starting to get the breakup of the cartilage rings, and we have more smooth muscle. So we can, these are the bronchi that we are easier able to change the diameter, and we change the diameter of those. That is going to have a bigger effect on our flow of air. This is where, for instance, where we talked about if you have anaphylactic shock, that histamine causes a constriction of the airways, an increase in the mucous membranes here, dramatically increasing the resistance, and suddenly, right, that kid can't get air into their lungs anymore. So what do? You give them a shot of adrenaline, and that adrenaline dilates the airways, increasing the diameter, decreasing the resistance, and increasing the flow, hopefully keeping them alive. So it's in this mid-sized bronchi where we can have the greatest effect on the flow of the air by affecting the size, by affecting the resistance. All right. So as resistance increases, breathing becomes more strenuous. And as we talked about, the type of things that can increase resistance is our parasympathetic nervous system. We know it constricts the bronchioles, increasing the air resistance. Whereas conversely, epinephrine, our sympathetic nervous system, dilate the bronchioles, reducing the air resistance. So that change in the diameter can be influenced by these types of chemicals, like the histamine, like the sympathetic nervous system, which releases acetylcholine, like the epinephrine released from our sympathetic nervous system. Change the diameter, you change the resistance. All right. We talked about this with blood vessels as well. Remember, we talked about how tiny changes in the in the diameter of the blood vessel can have major effects on the resistance. And it's the same thing here in the airways. All right. Questions on that? Yeah, there's more terminal bronchioles to disperse the flow. So many, many more of them. So even though each individual one may have a high resistance, when you have a million of them, resistance is very low. All right. Hold on one second. Okay. All right. So we've talked about moving air into and out of the lungs and how we're going to do that. And as we've also talked about, everybody's volumes are going to be different because everybody has a different shape to their thoracic cavity, a different volume to their lungs, different lung capacity, different lung health, different elasticities, all these different factors that can influence and affect these respiratory volumes and capacities. Luckily, then, we are able to measure these things using a machine called a spirometer. Now, back in ancient times, and by ancient times, I mean when I was in grad school, a spirometer was an incredibly technical piece of equipment. It was a large bucket that was filled with water. And inside of that bucket filled with water, you put a second bucket turned upside down. That second bucket would have measurement marks on it. And then you would take a third technical piece of equipment And that third technical piece of equipment would be a garden hose. And that garden hose you would put into the first bucket and into the second bucket. Then what you would do is you would breathe air into the spirometer. As you breathed air into that spirometer, it would produce bubbles. Those bubbles would fill the second bucket, causing the second bucket to move upward. And as the second bucket moved upward, you would count what hash marks were located at the level of the water, and that would tell you the volume of air that you moved. And in that way, you could see how much air was moving out of your lungs. All right? Could you necessarily use this to tell how much air you could bring in? What do you think? No, right? This hose was not something you ever wanted to suck on, right? Because then you would be swallowing all that water. Absolutely not. So it was not a very sophisticated piece of equipment. In the classroom, we have some very cool spirometers that can actually measure air moving into and out of your lungs. But unfortunately, we don't get a chance to play with that here. You do have some physiology things that you'll get to play with. So you'll get to talk some about those volumes. But what we need to talk about are these respiratory volumes and capacities, what they mean, how they relate to each other. Are we going to provide numbers for them? Yes. Are these numbers that you necessarily need to memorize? The numbers for the respiratory volumes or capacities, do you think they're numbers you need to be able to memorize? So when I say that you take a normal resting breath, is every single person in this class going to take in the exact same amount of air with a resting breath?
No.
No. So when I give you what the average number is that number really meaningful?
No.
No, especially when there's only 24 of us here. With 24 of us here, it's quite possible that nobody here in the class right now actually takes in what the exact average amount is. So I will give you numbers because I think it's good to have the relative idea of a size, whether something is 500 milliliters or whether something is 5,000 milliliters is something that is significant. But you don't necessarily have to memorize these numbers. What you do need to do is memorize and understand their definitions and how they relate to each other. So we'll do that as well. But like I said, the reason we don't have to worry about memorizing these numbers is because everybody's numbers are going to be different. All sorts of things, your age, your body size, your gender, your physical condition, illnesses, all sorts of factors can modify and affect these capacities. So these numbers, these average numbers that I give you are aside from their relative size, are relatively meaningless. But what we do need to do is understand them. And in fact, there's not just one or two. There are 10 important volumes and capacities we need to be able to identify and define. All right. Now, let's talk about one of those spirometers. If we were doing this in the classroom, let's go back to our whiteboard here and do one of these exercises. So what we would have is a graph. Looks a little something like this. Anytime you have a graph, you want to label your axes. So we have time here on the bottom, and up here on the side, we have the volume of air that would be breathing. And what you would do with one of these spirometers is you would hold this spirometer, and while you're holding the spirometer, you would take 3 normal breaths. After that third breath, you would take a maximal inhalation. Fill your lungs as quickly and as fully as you possibly can. And then you will breathe out as quickly as you can. emptying your lungs as rapidly as you possibly can. And then you'll go back to taking 2 or 3 normal breaths. Now, if you were to do that, what would happen is you would see a curve that would form that would look something like this. Inhale, exhale, inhale, exhale, inhale, exhale. Maximal rapid inhalation, maximal rapid exhalation, and then back to your normal inhalation and exhalation. This is what your graph would look like. And the nice thing about this is once you did that, you would actually be able to use the computer to calculate those 10 important volumes and capacities. So let's do that. The first capacity, so let's do that, and let's do that, and let's do this. The first capacity basically is the amount of air you bring in with a normal resting breath. So basically, we have to go from the top of our curve here down to the bottom of the curve here. This value is what would be the volume for your normal resting breath. And this volume is what we call the tidal breath or the tidal volume. There, there. The tidal volume is the amount of air you breathe in and out during a normal resting breath. All right. Questions on that? All right. Now, notice when you are taking that normal tidal breath, are you filling your lungs to its capacity? No. Clearly, as we can see here, we have an additional volume or additional space in our lungs that we are capable of filling with air. This is the max volume of air we're able to get in. So the next volume we would be interested in is how much extra space do we have in our lungs from that normal breath to be able to add more air into our lungs. So obviously we need to go from the peak here, but we want to know the amount above the normal breath. So do we want to measure from down here? No. If we want to know above the normal breath, we have to go from the top of the peak because this is what we normally take in. And then this volume here is the extra space that we have for extra air. And we call this the inspiratory reserve volume. This is the amount of space we have in our lungs that we could fill with air if we need to.
So it is the difference between maximum and normal.
Correct. The difference between the maximal inhalation and the normal inhalation. That is correct. By the same token, when we take a normal exhalation, when we do that normal breathing out, are we emptying our lungs? No. So notice we're not emptying our lungs at this point. There is additional air in our lungs we are able to move out. And so this volume, all of the extra air we have in our lungs, that we could move out if we wanted to, right? If we needed to, we could move that air out. That volume is our expiratory reserve volume. Oops, and I want that to be blue. This is all of the extra air we could move out of our lungs if we wanted to. All right, with me so far? Now, when I've moved as much air as I possibly can out of my lungs, are my lungs completely empty at that point? No, they're not completely empty. We don't want them to be empty, right? As we talked about, if they're empty, they're going to collapse. And that would be a bad thing. We don't want them to collapse. So luckily, even after I've moved out all the air that I possibly can inside of my lungs. So great question. So again, this was put to me privately. So if you take a normal breath, think of it this way. If you were taking a normal breath in, out, in, out, in, out, and right after you took in a normal breath, I told you to exhale as much as you possibly could. Would you be able to do that? Yeah, you could do that. You don't have to take a maximal inhalation to take a maximal exhalation. By the same token, you can fill your lungs to capacity and then just let the air come out too. You don't have to expel all of it if possible. Yes. No, you would just, so the question is there a name for that? No, you would be expelling your normal expiratory reserve volume as well as your normal tidal volume. But the point is, when you've exhaled as much as you can, our lungs are not completely empty. There is still a volume of air still in our lungs. And that volume of air still in our lungs is called the residual volume. So notice 4 important volumes of air, right? Our tidal volume, how much air we move with a normal resting breath. And now we can put a value to it, about 500 milliliters. Our inspiratory reserve volume, how much additional space we have for our lungs above what we normally take in. Our expiratory reserve volume, how much air we have in our lungs that can be moved out beyond what a normal tidal breath would be. And our residual volume, that amount that no matter how hard we try, right, unless you've got one of those steamrollers, you're not going to be able to force that air out of the lungs. So these are our 4 important volumes. And again, while we'll put values to them, so this one is, let's make it small, 500 milliliters. This one here is 3,100 milliliters. This one here is 1,200 milliliters. This one here is 1,200 milliliters. Is it vitally important that you memorize these numbers? No, but it'll help us to relate these things to each other when we talk about our other capacities. Okay? So now that we have these 4 volumes, we can start putting them together to make capacities. As we put these 4 volumes together to make capacities, what we'll see is, and again, the reason I put the numbers here is because we could do the math of the equation to figure out what the average of these would be. But more importantly, if I gave you any 4 numbers for this, should you be able to do all the calculations necessary for all of the capacities? Absolutely. So let's talk about the first one. The first capacity I want to talk about, and let's go with purple for this one, is our inspiratory capacity. The inspiratory capacity, whoops, is basically how much air you are capable of inhaling. So if you think about it, that inspiratory capacity would be the air you normally bring in with a normal breath. So that would be your tidal volume, plus all of the extra space of air that you have to bring in air, your inspiratory reserve volume. So what would the average inspiratory capacity be? $3,600, excellent. So that capacity, purple line, this one here, so there to there, that there is our inspiratory capacity. All right. Questions on that? All right. Notice if I take a maximal inhalation and a maximal exhalation, that would be the total amount of air I would be capable of moving. And that total amount of air I would be capable of moving would be what we called the vital capacity. The vital capacity is the total amount of air that I am capable of moving. For that, of course, would be the tidal volume plus all the extra air I could bring in, my inspiratory reserve volume, plus all of the extra air that I had in my lungs that I could move out, my expiratory reserve volume. And if I were to do the math with the averages, what would the average vital capacity be? Someone got ahead of me. 4,800 milliliters. Excellent. All right. So far, so good. Now, what color can I use for this? Let's use the dark green for this one. When I take a normal exhalation, my normal resting breath, as we know, I have not removed all the air from my lungs. Just a normal breathing out. I have not removed all the air from my lungs. There is still all this air left in my lungs. All this air left in my lungs is the expiratory reserve volume plus the residual volume. And what would that average be? $2,400. Notice this 2,400 milliliters of air is air that is still in my lungs even after I've breathed out. And if it's in my lungs, that means it's in my alveoli. And if it's in my alveoli, can it be undergoing gas exchange? Even though I just breathed out, can the air that stays in my lungs still be involved? We've got a name for it. I'm getting to it. Could it still be involved in gas exchange? Yes, that means it could still be doing work. Even after I take a normal exhalation, this air that remains in my lungs can still be doing work. And that is why this is called the functional reserve capacity. It is the amount of air that stays in my lungs after a normal breath out that can still continue to do work. And one more. As I mentioned, the vital capacity is the total amount of air that I can move into and out of my lungs. But is that the total amount of air in my lungs? Oops, hold on. I want that to be dark green. No. So notice I can actually calculate the total amount of air that would be in my lungs if I took a maximal inhalation. And that is my total lung capacity. Of course, I need this to be black. Total lung capacity. If you think about it, there's two ways I could calculate this. This is obviously all of my volumes together, tidal volume plus inspiratory reserve volume plus expiratory reserve volume plus residual volume. Or if you think about it, it could be my vital capacity, the total amount of air I'm capable of moving plus my residual volume. Either way, when I put them all together, what is my average total lung capacity? Six 1,000 milliliters or 6 liters. The average lung capacity is 3 2-liter bottles. All right, so you think about on a good Friday night, you're running to the store, buying 3 2 liters Purple Passion for you and your buddies to drink on Friday night. Those 3 2-liter bottles that you grab, that is your total lung capacity. So notice, as we go back here, we have that inspiratory capacity. That is the amount of air I'm able to take in with a maximal inhalation. My functional residual capacity, how much air is left in my lungs after a normal exhalation that can do work. My vital capacity, how much air I'm actually capable of moving in and out of my lungs. And a total lung capacity, how much air I'm capable of getting into my lungs, and it's about 6,000 milliliters. And again, do you have to memorize these numbers? No. But do you need to know their relationships? Yes. If, for instance, on an exam, I were to say that an individual had a tidal volume of 650 milliliters, they had an inspiratory reserve volume of 1,200 milliliters, and they had an expiratory, well, pardon me, and they had a vital capacity of 4,000 milliliters. As at part one of your essay questions, could you be able to tell me what the expiratory reserve volume is? What would it be? There we go. 2150. Perfect. All right. So you need to know these equations. You don't have to memorize these values, but you need to know these equations because these equations are important. How these things relate to each other are important. So I can give you any random numbers I want. and you should be able to figure out the relationships and give me other values based on the ones I give you. All right, so know the definitions, know the equations. Any questions on any of that? No one has any questions? Very disappointed. I'll wait till the question I want comes. Ah, that's the question that I wanted. Aren't there supposed to be 10? And I've only given you 8 volumes. Careful, I've only given you 4 capacities so far and 4 volumes. But there's supposed to be 10 important volumes and capacities you need to know. Absolutely. And the reason there are 10 is you are correct. We are missing 2. And the 2 we happen to be missing all relate to this volume right here. Tidal volume. What is the tidal volume again? Someone define tidal volume for me. Excellent. It's the amount of air you move into and out of your lungs with a normal resting breath. Excellent. Now, when you take a normal resting breath, the goal of that normal resting breath is to get the air to your alveoli so that gas exchange can take place, right? Isn't that the whole reason we bring air in when we take that tidal volume, to get it to the alveoli so gas exchange can take place? Is that the goal? Yeah, absolutely. But here's the question. If I'm bringing in 500 milliliters of air, is all 500 milliliters of that actually getting to the alveoli? No. Some of it only gets as far as my nose. Some of it gets as far as my larynx. Some of it gets as far as the primary bronchi. Some of it gets as far as the tertiary bronchi. Some of it gets all the way to that terminal bronchiole. If you're in that terminal bronchiole, if you're that little bit of gas in the terminal bronchiole, you can see the alveoli from there. But do you get to the alveoli? Do you get to participate in gas exchange? No, if you're in that terminal bronchiole, there's no alveoli there, and you don't get to participate in gas exchange. So of this tidal volume, not all the air gets to the alveoli. The amount of air that doesn't get to the alveoli is called the dead space volume. Whereas some of the air, not all, but some of the air gets to the alveoli. And the ones that get to the alveoli get to participate in gas exchange. And that gets to gas exchange is called the functional volume. So notice, oops, that didn't work. There we go. Of that tidal volume, about 150 milliliters of it doesn't make it to the alveoli, doesn't get to participate in gas exchange, and about 70% of it gets to the alveoli and gets to participate in gas exchange, and that's the functional volume. So the dead space volume, and again, for every single person, is the dead space volume going to be 30% of the air and functional volume going to be 70% of the air? No, it's not going to be that way for everyone, but for everyone, is the functional volume, is for everyone the functional volume plus the dead space volume equal the tidal volume? Yes. So the 30/70 is an average, but the two together equal the tidal volume. And again, know the relationships, know the functions. Great question. The air that doesn't reach the alveoli doesn't get to participate in gas exchange, but it is filling the spaces so that there isn't a void. You know, when you take a breath, there isn't suddenly a void of space in your nose. If there was a void in space in your nose, your nasal cavity would collapse. So the air in the conducting pathways help to keep those conducting pathways open. They just don't get to participate in gas exchange. So there you go. Clear that. Here we have those volumes and capacities. Again, averages. Notice I gave the averages for males, the averages for females are different. But again, we don't care about these averages. What I care about is their relationships, how you would calculate them. Understand how these things relate to each other. Remember their definitions, remember their relationships. And remember also, this is just about breathing. Do we move air into and out of our lungs for anything else? Let me repeat that. Do we move air in and out of our lungs for anything else? Yeah, like speech, right? Absolutely. Or there are other non-respiratory gas movements, not just speech, but coughing and sneezing, which again are protective mechanisms to help to clear the airways. Crying can cause variations and changes in our air movement. Laughing, hiccups, yawning, all of these are examples of ways that we move air into and out of our lungs that don't involve actual gas exchange. They're serving some other or some unknown function. Yawning is a perfect example. We still don't fully understand why we yawn. Right? We know it's not, we originally it was thought that your oxygen levels must be getting low. So it's a way of increasing oxygen levels, right? But we know that's not the case. As it says here, it is a large inhalation, so it can help to inflate the alveoli. So it may be a mechanism to help to increase alveoli activity, increase surfactant activity. But one of the weird things about yawns are very social. If you're hanging out with your buddies and one of them yawns, what happens to everybody else? They yawn too. So why that yawn is contagious is not understood. That it's one of those really interesting things they've actually studied too, because only real yawns are contagious. If someone fakes a yawn, right, that's not going to make you yawn. And what's amazing about that is it's not even the facial expressions or anything else. It is the sound of it. They have actually done, talking about it, May, they have actually done studies where what they will do is they'll take somebody and their significant other. And what they'll have their significant other do is pretend to yawn and then actually yawn. And they will play the audio recordings of those for their significant others. And the fake yawns won't trigger a response, whereas the real yawns are much more likely to trigger a response. So even just the sound of it, there's something about the sound of it that makes it that social interaction. So again, what the heck a yawn is and why it's happening is something we don't understand, but it's really interesting. But again, it's one of those examples of a non-respiratory movement of gas. All right. Questions on that? All right. Believe it or not, that's actually all I have for you today. Like I said, normally this is a lecture where we have a lot more physiology in the lab that we get to play with, so I don't have any more to talk about. So I'm happy to answer any questions about anything we've talked about. up to this time. If there's anything that's confusing or anything you want to go over again, I'm happy to do that. But this is actually it for the new material that I have. I don't actually have any other new material that I want to cover for today. The rest we will save for tomorrow. So if nothing else, you get done a little bit early. So if you haven't voted already, now you truly have no excuse. Get out and vote. Have your voice heard. Or at least be home by 4 o'clock, because at 4 o'clock is when the results will start coming in. And who knows what's going to happen then. All right. Questions on any of that?
I have a question.
Yeah, go ahead.
So the maximum capacity of the air that we inhale is including also the air that doesn't go to alveoli, right? It's in the nasal cavity, in the trachea.
Yes, so absolutely. If you're talking about the inspiratory capacity,
Yes, yeah.
right? This inspiratory capacity includes, because again, it includes the tidal volume. So it would include all of the air that doesn't make it to the alveoli, and then all of the air that does get to the alveoli.
Okay.
Oh, great question. So that's a great question as well. So let's go back to here. So in your modified mastering A&P, you have a link to a study area. And this is the study area. This is where you're going to do your physio-exis, for instance, right? This is where your practice anatomy lab is and all the things that are associated with this. A lot of good resources in here, but sometimes the ESO, again, the interactive physiology, which is what I was talking about, was right here. We click on that. And notice here are respiratory things. So that is one way to find that. But if you really want to maximize the studied tools that are here for you, the easiest way to do that is to study by chapter. If you click the study by chapter and go to the chapter you're interested in this case, the respiratory system, here's where you'll find the chapter quiz. Here where you'll find a chapter practice test to help you with this material. And then here are all the sections. Some of it is just the e-texts, but notice this is where the interactive physiology is. Another interactive physiology, a flashcard maker, a more interactive physiology, some clinical cat studies, gas exchange videos. All of the resources that are here are all in one location for this. So you can find all this, including the PhysioX exercise we're responsible for, a tutor guide, all of those things. So it's an easy way to see all of the resources that are available. I'll be honest, I don't think the respiratory system is I think it's a little bit more straightforward. What's going to be, I find a little bit more challenging of the two systems. I think the urinary is a little bit trickier. But again, you have all these great resources that can really help you understand how the movement of the salt and water, movement of the proximal convoluted tubule, glomerular filtration rate, all these things that we're going to talk about. There's some great resources here. I assigned the cardiovascular, one of the cardiovascular ones to you, the one on the ECG, as a carrot to make you aware that that was here, but that was a while ago. So you may have forgotten these resources were here. So if that's the case, I want to encourage you to come back and make sure you're taking advantage of, especially if you paid for these things. These are resources that can help you to be successful. I know it's easy to focus on just the things that you have to turn in for a grade, but sometimes having these different modalities to see and hear the information can be really great. That interactive physiology is a 5-minute video that does a really nice job of showing a lot of the things that we just finished talking about. The Boyle's Law and some of the other things on there as well. It talks a little bit about the control mechanisms that we're going to talk about. So it is a really great resource, and there are more in there as well. So yeah, by all means, take advantage of those. All right. Any other questions? All right, excellent. In that case, enjoy the rest of your day. Again, this is not a day off. This just means that you have more time to study this stuff independently on your own. Make sure you're doing the work that is going to help you to be successful. Oh, excellent. And so the practice tests and quizzes are something that are helpful. Yeah, absolutely. Excellent. Yeah, again, taking a test is a skill. So the more you practice it, the better you will be. I like visual stuff. The art labeling activities are things that I always find fun too. I like the animations and the videos. There's a lot of great things in here. So yeah, by all means, take advantage of it. Help you to be successful. All right, guys, enjoy your rest of your day. I will see you on Thursday.